Okay, for this one, we perform the same 3 steps. So step number 1, is this proper or improper? We have a degree 3 in the denominator, which is higher than the degree of numerator, so we're good to go. And now we go to step 2. We take the denominator, I'm going to write it here in the bottom. I'm going to factor out an x, so I have x squared plus 2x plus 1 inside, which then factors to, I can put 2 parentheses, 1x on each side, plus plus is plus plus, and then 1 plus 1 is 2, and 1 times 1 is 1, and this further simplifies to x plus 1 squared, which is very important to put it this way because now we have n explicitly being written, which is always good. Okay, so now we can go on to step 3. So we realize that we actually have 3 linear terms. We have x plus 1, and then x plus 1 squared. So let me go ahead and write that. We're going to have a, because it's linear terms, a over x plus b over x plus 1 plus c over x plus 1 squared. Now the next step involves, I'm going to make a little bit of space here, involves smiley phase, or adding 3 fractions, which give me an x plus 1 squared, which I'm going to factor, times a times x plus 1 plus bx plus c times x plus 1. And then the denominator, which we already know is going to cancel, so we don't even have to write it down, but I'm going to write it just for the sake of showing you something interesting that's going to happen. As you can see, if you look at what we have on the numerator, we can factor out an x plus 1, which gets rid of this 2 and gets rid of this. And I can take one of those x plus 1s and cancel it out with one of the ones from the denominator. And now the remaining expression is exactly the same as what we had originally. You can also see it here. And now I can take the remaining part of the numerator and write it down. So a times x plus 1 times x plus 1 plus bx times x plus 1 plus cx, and that's equal to 5x squared plus 20x plus 6. And now we can try to find the values of a, b, and c using the method we used in the previous example. So notice that if I set x equal to 0, I'm going to get rid of the c, right? And then I'll just have a and b. So all that process, if you do all the arithmetic, you'll see that a is going to be equal to 6. If you set x to be equal to minus 1, you're going to be getting rid of both a and b, and so you'll end up with just the c, which will give you 9. And if you set x to be equal to 1, you already have the values of a and c, so you can get the b value with substitution, and b is going to be equal to minus 1. Verify this for yourself to see if it's correct. And finally, I can take a look at expression 2, which was this, use it as a reference, and say that 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x can be expanded into a, or 6, over x. B is minus 1, so minus 1 over x plus 1, plus c, which is 9, over x plus 1 squared. And we're done. Let's take a look at one final example. Alright, moving on with our partial fraction expansions, we have this problem, and our mission is to expand it into 2 smaller fractions. So let's do that. As I said in the previous examples, there's 3 steps I always want to do. Step 1 is to verify whether the expression is proper or improper. In this case, I have a degree 3 in the numerator. In the denominator, if we multiply everything out, I'm going to have a degree of 4. 4 is larger than 3, therefore it's proper. So we can move on to step 2. In step 2, our mission is to verify the denominator to see if we can factor it out or if it's irreducible. Now in this case, notice that x squared plus 2 is a quadratic, and if we try to factor that out, we're not going to be able to do so. If we use the quadratic formula, we're going to get imaginary or complex solutions for this particular expression. And that means that the only way to factor this out is to use complex numbers. Remember that we don't care about this for this course, so for us it's just an irreducible quadratic in terms of real numbers, okay? And now we can go ahead, now that we've verified step 2 procedure, we can go to step number 3, which is to expand and proceed to find the missing variables. So this is going to be equal to x squared plus 2, and then I need another one that's going to be x squared plus 2 squared, because our n is equal to 2. We need 2 new fractions. And since these are irreducible quadratics, if we take a quick look back in our table, the numerators need to be linear terms instead of just constants. So I'm going to put an ax plus b here and a cx plus d over here. Now that I have expression 1 and expression 2, I need my expression 3. Refer to the previous video if you want to know what I mean by expression 1, 2, and 3. So ax plus b using smiley face times x squared plus 2 squared plus cx plus d all times x squared plus 2 over x squared plus 2 x squared plus 2 squared. Now we know from the previous video that I don't really need to write down the denominator because it would always get canceled, but I'm writing it because it's important to know that if you compare the previous one with the new one, there's an extra x squared plus 2 that we need to get rid of in order for everything to make sense, and that just means that I need to factor an x squared plus 2, which is exactly what happens. So when I do that, I get rid of this square and I get rid of this term, and therefore these cancel. Also these, but I don't really look at that because of what I said from the previous video. I'm looking at expression 1 and 3. Now when we do that, we have, let me change colors, 8x cubed plus 13x is equal to ax plus b x squared plus 2 plus cx plus d. In order to solve this, what I'm going to do first, since I have 2 variables here, is I'm going to distribute everything, which gives me ax cubed plus 2ax plus bx squared plus 2b plus cx plus d, and then same thing on the left hand side. Now I could try grouping the a's and the b's to see if we can solve this, but what I'm going to do in a case like this where it's a little bit more complicated is consider this as a system of equations. So I'm going to create, there's 4 variables, a, b, c, d. I'm going to create a system of 4 equations, and this is how I'm going to do it. I'm going to treat each exponent, each group of exponents individually, okay? So what I mean by that is I'm going to start with x cubed first. So when I do that, I have 8x cubed equals ax cubed, okay? Just the cubes. And naturally, the cubes cancel. So I don't really need to write them. So I'm just going to write 8 is equal to a. And as you can see, we already have the result for what a is. If we keep doing that, then squares, there's no squares on the left-hand side. We only have a bx squared. So bx squared, or I don't even need to write the x, b is equal to what? Well, there's nothing on the left-hand side, so b equals to 0, and we have our result. Now for x to the first power, there's 1 over here, and there's 1 over here and 1 over here, meaning 13 equals 2a plus c. In our final equation, x to the 0, or just the constants, we have nothing on the left-hand side, so 0 equals, and on the right-hand side we have a 2b plus d. Now we already know that b is equal to 0, which means that d must also equal 0. And for this last expression, we already know that a is equal to 8, so when we substitute, we get that c is equal to -3. And now that we have the values for all the 4 variables, we can go ahead and write out our final answer, which is that 8x cubed plus 13x over x squared plus 2 squared expands to ax plus b. There's no b, so just a. So 8x over x squared plus 2, and then plus, there's no d's, just the cx. C is negative, so I'm going to say minus 3x over x squared plus 2 squared, and we're done. And as always, you can verify whether or not this is correct by, in this case, subtracting both fractions and making sure you get the same thing as here in the left-hand side. So by now you should be pretty decent at solving partial fraction expansion problems. Now we are ready to solve integrals that require this technique. So I'll see you in the next video for that.